Welcome everyone to the 8th edition of the DHC Plus Talks. For anyone who has not attended one of the previous editions, these talks are a series of webinars where we discuss a variety of topics in an informal setting. So grab a coffee in your favorite mug and take a break from your regular routine, whether that is home office, child minding, or maybe some of you are already back in the office. You can participate in the discussion by asking questions to the panelists via the question box to the side of your screen. The webinar will be recorded and the presentations will be made available on the Euroheat & Power website. And if any of you have follow-up questions following the webinar, please feel free to write to us on LinkedIn. The topic for today is 5th generation district heating and cooling and is brought to you by the REWARDHeat project. This new generation of district energy networks represents the next step in the evolution of the sector and is vital to the pursuit of fully decarbonised heating and cooling. My name is Jack Corscadden. I work for Euroheat & Power, the international network for district energy, as part of the DHC Plus technology platform. DHC Plus is the research and innovation hub for the district heating and cooling sector, involving a variety of stakeholders from industry, research, and academia. Our activities consist of research and business support for our members, including extensive networking opportunities, education and training, including the DHC Plus Summer School, advocating for district heating and cooling in Europe, and we also function as a knowledge hub for all resources linked to district energy. European projects are a cross-cutting element across all of our activities and are at the center of everything we do. So there is no set definition of 5th generation district heating and cooling. Broadly, it can be described as demand-driven smart grids delivering low temperature heating and cooling. When we talk about 5th generation networks, we include all technologies and network configurations operating at low temperature, below 60 degrees Celsius, and neutral temperature between 10 and 30 degrees Celsius. These smart networks are capable of integrating diffused, renewable and waste heat sources, leading to an optimized, flexible and increasingly decarbonized system that is highly connected to the electricity grid. So I will now introduce you to our speakers for today. Our first speaker will be Roberto Fedrizzi from Eurac Research, who is the coordinator of the REWARDHeat project. Roberto has worked in the renewable energy sector since 2001 and is active in the field of sustainable heating and cooling systems for single buildings and district heating networks. He tells me that he has gotten through the long lockdown in Italy by gardening, where he lives close to the mountains. We will then hear from two of the demonstrators of the REWARDHeat project. Firstly, Herman Eijdems, who is the Director of Research and Innovation at Mijnwater, and he will present the Dutch demonstrator site. We will then hear from Keim, a project manager at EDF, who will present the French demo case. And finally, we will hear from Maria Victoria Cambronero Vazquez from Acciona, who is the coordinator of the We District project, one of the sister initiatives of REWARDHeat. Maria Victoria lives in Spain with her family and has been working in the renewable energy sector since 2009. So I will now ask all of the presenters to turn on their webcams. So as is tradition during the DHC Plus talks, each of the speakers is asked to show the audience their favorite mugs. So this is my favorite mug. The light is quite bright, but as you can see, it says, "I'd rather be eating cake," which is true for the vast majority of the time. And so, in order of the agenda, Roberto, can you please show us your mug? Thank you. Herman, have you got your favorite mug? I think your microphone is muted.
Yeah, this is my favorite mug, and it's specific because you buy them for less than €1, and all my colleagues were taking the plastic cups from the coffee machine, and then I bought about 10 of those to give them all their mug and to do their dishes end of the day.
Great, I'm glad to hear that. And Christian?
Well, this is my favorite mug. But as I come from Italy, you might understand that we usually drink a coffee more smaller than that, no? So anyway, I love it because it's from Beijing. It's from a fantastic district called Nanluxian, which was very vibrant about culture and restaurants and bars. But unfortunately, it doesn't exist anymore as it was, because it was kind of formalized. So it's a little bit a pity, but well, I remember always from that fantastic 5 years I spent there, which were great, professionally speaking and also personally speaking. Because my 2 kids of 3 were born there. The other one was born in Spain. So well, that's a pretty important cup.
Great, so there's real history behind the mug. And Maria Victoria?
Yes, here is my favorite tea mug. Well, maybe it's not very beautiful, but I like the message, although it's in Spanish, but I can translate, of course. It says, smile, today will be a perfect day. Well, I think it's beautiful.
I think today is a perfect day in most of Europe. And so thank you, everyone. I will now ask all of the speakers to turn off their webcams. And Roberto, can you please start with the first presentation and share your screen?
Yep. See if you can see my screen.
Yes, we see it.
Okay, good. Good afternoon all. And just to be sure, in case my boss is connected, I didn't spend the entire lockdown gardening. I also made some work in the meantime. Apart from this, REWARDHeat. The product is about smart energy networks, as Jack said earlier before. And the background of the project was that we all know that the European population lives in cities and towns, or mostly lives in cities and towns. And if we want to solve energy-related problems, we need to be able addressing this kind of population, mainly. Luckily, what happens is that there is a lot of energy available in cities. There is a lot of low-grade waste heat, which is available, which is diffused in the urban context, coming from air conditioning, from refrigeration, from sewer pipes, and so on and so forth. But there is also a lot of renewable energy available because, for historic reasons, cities and towns are born along rivers and lakes and seashores, as we will see later on by our demonstration partners. And obviously, we don't even mention the solar source. So there is a lot of energy which we should be able to use and exploit. So our vision is that we should use energy networks, energy grids to make this bunch of energy available to everybody. And what we want to explore is how to harvest low-grade, low-temperature waste heat and renewables. So what is available in the urban context and lower than 40 degrees C, for example. And to do so, what we want to do is what we believe is important is to, first of all, this is not sufficient, but first of all, we need to work with district heating networks that have supply temperatures lower than 60 degrees, for sure, and this is the definition of low temperature network, at least. And we want to explore what happens when you go down to even 10, 20 degrees C supply temperature. Obviously, this is the basis, but it's not sufficient. What we are going to do is to, on the one hand, develop planning tools, pre-designed tools, and this is going to be based on analyzing what are the best configurations, best topologies, best sizes, and so on and so forth, that you can use to make these kind of networks, low temperature networks, suitable from the technical and from the economic point of view. So we want to gather planning schemes. We want to build a database based on that analysis, and then we are going to work on pre-design tool. Again, this is not going to be a new tool, a brand new tool. What we want to do is to build on previous tools developed within other European projects, like the planning tool, for example. And apart from this, what we want to do is to look also into technologies. So we want to develop enabling technologies like substations, obviously. That is key to the success of these low temperature networks. They must be substations that are specialized to the network, to the supply temperature of the network, and since they are more expensive in general than conventional networks, then we need to work on prefabrication and industrialization, because in this way you can work on say economies of scale, and you can lower the prices, the costs for the investor. So we are going to work on a small size substation that you can install or that you would use at user site, as single building site. But we are also looking at the problem from the other perspective. So we are also trying to understand how to industrialize, how to systematize the design of large scale energy centers. So what you would have at central level. And what we want to understand is what is best used in different applications. So either the small scale or the large scale substations, or again combinations of the two in different cases. Apart from substations, we have activities also on developing new pipes that are adapted to lower heat losses in this kind of networks, so with low temperatures. And indeed, we want to work on thermal storage. So again, different levels: single customer, single building, up to the network size, overall network size. Meaning that we are working on how to install and how to exploit, how to best use thermal energy storages in the single substations that are installed at customer side. But we also want to see how to use high temperature, large size storages, like the one that you see in the small picture, in the small sketch on the bottom of the page, that can eventually be charged during some part at high temperature, during some parts of the day, and then the energy can be used at lower temperature, distributed at lower temperature during other parts of the day when the energy is needed. And again, indeed, we want to work on seasonal storage. And after initial discussions, it seems that the demonstration partners are orientated or focused on developing borehole storages. Apart from this, these are single technologies, so substations, pipelines, storages. Again, they are the single units, the single components that are allow you to build the network, and they are going to be specialized, as I said before, to the low temperature configurations. But again, my perception of the entire project is that we need to have all these components working together in a proper way and in a meaningful way. Not only that we need to have them working reliably, but we need to give them an operation which is meaningful from different perspectives, as I would say before. So basically, all the concept of the smart network is based on smart metering on the one hand, so smart meters communicating real time, continuously to a data center, data mining platform that gathers all this information from many customers and then again a supervision software that on the one hand works on fault detection, but on the other hand mainly works on control strategies that allow to optimize the operation and integrate all the components one with another and integrate the network with the electricity grid, which is of utmost importance for us. Why is this? Because once again, everything works from the technical point of view, but you need to make sure that everything is feasible also from the economic perspective. Economics means, on the one hand, business models, and we are working on moving from a concept of heat as a commodity, so you sell kilowatt hours, to heat as a service. This is one of our mottos, meaning that we are trying to find ways in which heat is sold as a service for single customers, like for example providing them better comfort or better additional services in addition, to heat. But we try to also find business models that are useful, or services that are useful also for the electricity grid, in a way that it is again seen as a service, as a opportunity, not only for customers, not only by customers, but also by electricity providers, for example, or aggregators. And finally, again, we need to make sure that there is enough finance around to make the construction possible, which is, again, we need to look for public funding that is going to be there in the future, obviously, from Europe, from the single national governments. But again, our thought is that we need to find ways also to attract private funding. That is going to be really of most importance in the near future, if we want to upscale the demonstration projects we are running. This is about REWARDHeat in a few tips. We have 7 demonstration networks actually available or in progress. We are in the initial planning phase. There are no demonstration activities yet started. But again, we move from really low temperature networks, meaning neutral temperatures, like in Milan and what you are going to see in Toulon by EDF and Dalkia, to other networks that work at supply temperature between 55-60 degrees. And what we are trying to do is to have a number of combinations of waste heat use, heat pumps use, central, decentral. And again, the final goal is to try to see and compare what are best combinations of technologies, renewable energy sources, and waste heat in different climatic conditions, applications, and under different legal boundary conditions, again, that you can find here and there in different member states. I don't want to spend too much time on this. You are going to see 2 very interesting demonstration networks in a minute. Thank you for listening to me. I reported here in the presentation also the address of the website. That is not yet in place. Hopefully, it is going to be in place between today and tomorrow. So please stay tuned, and again, follow us on the website and on different channels, social media, that we are going to use through the project elaboration. So thank you again, and Zach, back to you. Hopefully I was not too long.
Thank you very much, Roberto. I think one of the most exciting aspects of the project is the application of thermal storage technologies, which of course has major implications for sector integration and the development of renewables. But Roberto, we already have a question, if you'd like to answer it now, so, from one of the audience members. So, is there an estimation of the cost of the new substations when they are eventually commercialized?
Yeah, that is, say, it depends on the, so to answer directly, no, it is that there's no commercial price yet available. And this is because we say it is in the commercial price is going to depend strongly on the configuration we are going to decide and on the, say, economy of scale again that we are going to reach. For now, you can imagine that if you do not industrialize a substation that includes storage and heat pump, so a small size one, and again, for a single building, the cost of the installation might be in the range of 800 euros, 1,000 euros per kilowatt hour, so per kilowatt installed, sorry, which is quite high, and that is why we want to work on reducing this price. There is quite some more experience by Mijnwater on this, maybe, and I do not know if Herman is available to give an hint on this.
Yes, hello, this is Herman Eijdems. Yeah, I think we have some also some trouble, but if we have some really rough figures, then we could say a heat pump will cost you about 1,000 euros per kilowatt. And if you go to substations in buildings, then it might be around 2,000 to 3,000 euros per kilowatt. But as you also said, Roberto, there are many ways to optimize these costs still ahead. So I think we can do much better prices in future.
Great, thank you very much both for your inputs. We'll now move to the second presentation. So Herman, can you please share your screen?
Yes. So I just go on in my presentation. Let me see if I can go forward on my sheet. Is it moving? Does everybody see the next sheet?
Yes, you're on the map.
Yeah, okay, great. Well, I'm working at Mijnwater in Heerlen. We are located in the very south of the Netherlands because that's the area where we had coal mines in the past. And those coal mines are flooded because they are no longer used. From this map, also you can see that we are in the very middle of Europe. So we have a very nice position to cooperate with all other countries around us. The idea is that if we go down in those old mines, if we go deep in the galleries and shafts, then we find a raised temperature from geothermal energy, which is going up to, in our case, about 30 degrees Celsius. And if we go higher in those high galleries, then we find water which might be 15 degrees Celsius. So we take both these sources from the abandoned mines and bring them to buildings and feed heating and cooling systems in the buildings with this energy. This is more or less how it looks underground. One of those galleries, a bigger one, which has had drains running in it. It's about 2.8 meters broad and 2.5 until 3 meters high. If we count all these voices sum them up for the Herman situation, then we find about 8 million cubic meters of water under our feet. And if we look at the amount of energy that is in this water, for 1 liter, we can calculate, we use the delta T of 12 degrees Celsius. So it would be 14 watt hours. But if we have a lot of that, like 6 cubic meters water would have the same storage capacity as is in 1 Tesla car battery. Actually, we started this at just taking heat from the very low galleries and bringing them to buildings and heat them in winter time, and then re-inject this return flow more or less halfway at 400 meters back in the ground. And then in summertime, we would switch over to a cooling system and take the cold water from the high galleries and cool the buildings and then return it also at the same spot. So this bubble in the middle would shift from left to right between summer and winter. This is graph is showing one of the main problems that we have, because I see this in many places, that on the one side, and that's the green line at the bottom, and we try to build and generate renewable energy like solar and wind and geothermal and biomass. And if we go in time and we generate more and more renewables, and on the other side, the yellow line, it's the energy consumption line, which is coming down if we save energy, like for dwellings and offices and all these sectors. And when they cross, we think we get a situation of energy neutral. And actually it doesn't work, because this two energy flows have to match in time. They also have to match in geographical in place, and also they have to match in temperature. So we have to take a few actions to get this picture right. Well, when we went on Mijnwater and this mines, there is a lot of energy in there, but actually it's still a limited resource. So that brought us to the 5th generation district heating grid, that we tried to make the grid on the ground in the city more intelligent, smarter, to use this energy better. And one of the things that we did about 10 years ago is that we switched from taking just heat and cold from the earth to also going to use it as a storage. So we made the hot bubble, which where we take energy in winter time and re-inject in summer. We have the cold bubble where we take the cooling in summer and re-inject in winter. We don't need to return well anymore, because now we have bidirectional sources where we can take and return water at the same point. Those wells, we have 2 red dots in this picture, which are 2 hot wells that we have in Herman, and then we have 2 blue dots, which are the cold wells. The return well is somewhere in between there, but we didn't show it. Those wells are connected by a yellow line, which is a backbone, and just carrying the Mijnwater from the sources to the customers. And we have the small white squares, which is basements, and connect this backbone to clusters, cluster grids. In the clusters, we don't have Mijnwater. The basements are exchanging energy from the backbone to this cluster grid. Actually, now we are serving 200,000 square meters in a public area of, it's about 500 dwellings and commercial buildings. This is the idea. So if a building is connected to this cluster grid and it needs cold, then it will pump will start running, and it will take cold from the cold pipe and re-inject heat into the hot pipe. If there is in the same cluster a building which needs heat, then there the pump also starts running, and automatically the heat will flow from the one building to the other one. If there is a net heat demand in this cluster or cooling demand, then it will go to the cluster basement and exchange this energy with the backbone. As we have 4 cluster basements now, it first looks if there is complementary energy demand from another cluster. If not, then we go all the way back to the mine and store it in the mine reservoir. This is also the idea if we go to 5th generation. So we see we have one axis where we have temperatures from maybe 0 degree up to 55, which are source temperatures. And then we have an aggregation level on the other axis. On the most left of this graph, it's the city level, and we want some kind of storage at the low temperature. We can take heat in the city. It might be an aquifer, it will give you 10 degree, and as we have Mijnwater, it will give you 25 degree, but it can also be sewage, anything. And you want to store this energy on the city level in a large buffer. From this point, we have to raise the temperature, and we do this weather dependent for mainly space heating, use central heat pumps for that, and also try to build a buffer, which might be around 30 to 50 degrees Celsius for a neighborhood or a district where we use this energy. From that point, we go to the buildings and individual and complexes. And at the building level, we have a booster heat pump where we bring it finally to the demanded temperature, like for domestic hot water, at least at 60 degrees Celsius. And also there we can have the small vessels, the boiler vessels, with which store this high temperature energy. So it's a buildup of multi-level and multi-aggregation level of sources and buffers, which you try to let them work together and reinforce each other. This is our grid in Ireland. We have the hot pipe, which is the red square, 25 to 28 degree, and we have the cold pipe, 16 to 18 degree. In this grid, we try to move from central planned ideas to decentralized installations. So we try to get as much energy plans and installations in the buildings itself, acting locally, and as such building a cloud of heat pumps and connections which work together. Just like in the IT, where we went from central servers to cloud systems, we try to do this with thermal grids also. If you look at the building, then we have a few steps. Left, we have the original energy demand, which is for a dwelling in the Netherlands about 20,000 kilowatt hours. Then we must do some savings in this energy, and we easily can do it, maybe 20 to 30%, which gives us a remaining energy demand of about 70%. If this building needs cooling, and we can reuse this cooling for heating in winter, then we add up a bit of cooling, but also find it regained in winter time as free heating energy, and add up waste energy, at best this low temperature waste energy from the city. So we reduce this remaining energy demand to more or less 30% of the original. Then in this grids, operating at 25 degrees Celsius, we have a very strong source for heat pumps. So we can get very good COPs of heat pumps, giving this heat demand and cooling demand. So actually we bring down the 20,000 kilowatt hours original demand through several steps back to maybe 2,000 kilowatt hours electricity. And that's an amount of electricity that we can deal with in cities. And we have enough roof area and enough area to make the 2,000 kilowatt hours from solar panels and any other green sources, but we never can do the 20,000 kilowatt hours. Well, then I have some pictures. This is the cluster basement. We make those basements prefabricated. We bring in skids, which are also prefabricated and more or less adjustable. We bring them in the ground, we cover them with ground, and then you see very little of it, and it's small disturbance of this environment where we have to do those works. This is about neighborhood. We could do a sector basement there and bring in also the heat pumps for a limited number of dwellings. Idea of how this kit could look like. Actually, we did the first sector basements just 2 months ago in the city of Brunson. This is the idea for renovation of high-rise buildings. So we need very easy solutions which do not disturb too much those buildings and those occupants, and which are more or less prefabricated modular. So we designed an installation column which could be placed in front of this before those apartment building and connect those dwellings within 2 days to our system. This is my final sheet. It's about a business case. So on the very left side, if we look at heat networks, they have a high amount of money they need to spend to buy fossils and to run those fossil plants. So if we go to saving energy and go to green generation, then we find that we switch from fossil fuel to electricity, only a bit of fossils anymore needed. And the next step is that we don't use any fossils anymore. It's the third column, the Mijnwater 2.0, all electric. And also we start to generate our own electricity by own PV panels, which are in the district heating system. And then we are working now to the 3.0, and then you only have a limited amount of energy variable prices, and you see that you have a big amount, 19 euros, maybe about 20 euros now per gigajoule, which is fixed prices, which is investment in sustainable infrastructure, and which comes available. So you have the space, you can invest about 15,000 euros per dwelling if you don't need to spend your money on buying fossils anymore. Thank you. That's was my story.
Thank you, Herman. And just very quickly, as we're quite short on time, there are 2 specific questions. So the first question is, have you had any problems with the water quality coming from the mine? And secondly, what is the long-term stability of the mining galleries, and did you have to reinforce the structure before flooding?
Yeah, well, it's easy questions for me. We didn't have a lot of trouble with the mine water. There is some gases in there, and we found out if we keep this water under pressure, at least 3 bars of pressure in the backbone, then we don't have any trouble with pollution of this mine water. We didn't use filters. I know other locations where they used filters and had a lot of trouble from those filters. Well, actually, if you just don't use it and just pump it around, it's running very well. And we are doing this over more than 10 years. So we have a lot of experience there. Stability of mining galleries, we never thought about that. And we did nothing about that because those galleries are closed. They put concrete blocks in the shafts already 50 years ago, so we never had access to the galleries. But the water, if you calculate what we are pumping out of this 8 million cubic meter, it's about maybe 500 cubic meter per hour. So those water flows are very, very low, and it's not really disturbing anything in the underground galleries or mining systems.
I'm muted. Thank you very much, Herman, for the succinct answer. So we will now move on to Christian for the 3rd presentation, and he will present the EDF demonstrator in the south of France. So Christian, please share your screen.
So I hope you see my screen popping up. Yes.
Yes, I see it.
I'm Christian Keim from EDF, and I'm presenting the demonstrator à la Seine-sur-Mer, which is actually operated by Dalkia, which is a 100% subsidiary of EDF. And we're doing this in a collaborative way in which each and everybody has clear its tasks, and it would be my colleague Karim Parpignon, which should have done this presentation. So I'm replacing her. So, L'Ascension, where is it? It's, if you know, Le Côte d'Azur, we're exactly there. We are nearby Marseille, about 1 hour drive. And as you see from the picture below, we are located just in front of Toulon, which is might be a little bit
Christian,
more known.
I think there's a slight delay. I'm seeing the overview and the first slide.
Okay, you want to do it for me? So ensure.
Yes, okay, I can share your presentation.
Yes, we have a pretty overcharged network in the district. Science they call it. Stop sharing screen. Up. I give you the hand.
Okay, can you see my screen?
Perfect.
Great. So you just say next,
one,
and I'll move to the next slide.
Yes, please. So as you have seen, where I was stuck, it was in Ascension. So we are in front of Toulon, which might be a little bit more known. And actually, this network, it's a public delegation of service. So public delegation of service means we operate this grid in the name of the public authority, the local authority, which owns this grid. Like everywhere in Europe, in water infrastructure, the electric grid, or others. So we have a 20-year contract. And the numbers I've shown you is actually what we have engaged in contractually with the municipality. So our challenge is to get it up to 75% of renewables and have a really low content of CO2 in this network, which for actually is actually the best, this low temperature network are actually these ones that can reach these numbers, except other high temperature like running on biomass or biogas. So really have to implement this one. So if we go to the next one, please. So you see a little bit the scheme of what this, how this works. Just to say that we didn't design this network. We got in heritage with this open call for tender 2 years ago. The network was built up in the early 2000s. So what we have is a first, let's say, loop. It's what we call the seawater loop. So we pump the water directly from the port at 4 meter depth. We pump it up. We have an exchanger and a pumping station, exchanger station. The seawater is repumped back into the sea at the same depth. And then we have this water through the exchanger. We have the low temperature loop or neutral temperature loop, we want to call that, because we are running about between 7 to 29, 30 degrees. We have this low temperature loop with clean water, so we have no problem of corrosion or anything, which brings them through the loop to the substations, the calories, the water, which is used to extract calories for heating, or we inject into the calories during cooling. And as you see, we have no production, centralized production, we have a decentralized production. So heat pumps are located at the substation level. And in some specific substations, we also have sanitary water, so we might have boilers, which were there before, that we have to integrate in it. So this is really the change of operation, which has to be understood, is that we don't have a centralized production, we have a decentralized production. And so we have to ensure whatever we use to operate the system is capable of dealing with this decentralization. And moreover, as you see, we put energy transfer. What you have to understand is once we pass through a customer, the water temperature afterwards, he might influence by rising or lowering this temperature for the next customer. So it changes COP in our heat pumps. And it's a pretty optimization problem. So next one, please. So this is the network as we got it. On the left side, so you have the pumping station, the exchanger station is about 5 megawatt installed capacity. And we have already our first customer, it's pretty interesting, which is the casino. So it's a casino really where you gamble. So this one has high cooling needs during the evening, even if not heating time or cooling time. So this one already exchanges calories into the network and influences all the other customers behind. And I'll put you on the right side, what we call the island. So there are these extensions which are underway. So if I put the dates of 19 and 2020, it's not when they will be delivered. It's that they started design and negotiation with the customers and works for some of them. So you see how this network will extend during time, and you have in violet the neutral temperature loop. And we have for the West Island, we have actually foreseen to create a centralized, let's say, substation because they have no cooling needs. So we ramp up the temperature about 20 to 55 degrees to serve the customer which actually is cool. So we have this play between the neutral network and some islands which are on the secondary level, which are on, let's say, medium to high temperature, depending on the definition. Next one, please. So this network actually introduced it into demo and the REWARDHeat project, which Roberto has presented. So we should retake a little bit the scheme I've just seen. Next one, please. Our very first objective is to connect all this decentralized system into a centralized SCADA system and put on top of that our system, which is developed by DF, which is called the Mix. Which is actually a system which, considering the constraint of the automation system we have on site, on the equipment we have on site, is able to do forecast of heating and cooling loads in a decentralized way and integrate optimization of decentralized system. As a second step, we want to go into these customers and integrate PV production into a certain one customer of them, and be able to use this renewable energy to run his heat pumps. This clearly has to be connected to a building energy management system, and we also look in the interest to install battery energy storage systems, so electrical storage, electrical battery, to store this energy for, let's say, if it makes sense, in this case, the casino, to store it for later on and be able to produce energy, green energy once it's used. We're also integrating the question about storage, which in the first case, we imagine to be centralized, but it's not so easy to get the land and the public land to locate an available space. So we are looking for distributing the storage maybe to a certain substations. And then number 3, next please. And actually I'm looking to integrate this also contractually. It means if we are by a customer, we're operating his PV, we're operating his storage, we have exchange of calories between them, I said before, try to integrate also that in let's say an energy performance contracting, which is an extension of what you do usually. So try to find new business models, how and how much, let's say maybe shared energy can be retributed and create win-win situation between the operator and the client. So next one, please. So just coming to the Mix. The Mix is actually a platform. It's a web-based platform which can be accessed from any terminal. Might be on site, might be on your smartphone, and it's actually divided in 2. We have a first module which is on the left side, which actually is used to design. So it's a design tool for the networks, in which we have integrated different models of the networks, and where Dalkia will be able to use a single and same tool to do the whole design process. And then we have the operation part, which actually interests us more. It's on the right side, and which we integrated the load forecast, the optimization of the network, and which is really sought as an exploitation platform, and which should integrate the performances. And a little bit in the longer term, actually this tool should be, by making this all accessible, all centralized, should really become a platform, a really important platform in which we can link design and exploitation, in which we can share data, we can share models, and so create really also as a knowledge exchange. Next one, please. So here I have an interface example of this platform, which I have installed elsewhere, but clearly not in the same way. It was a centralized one and a decentralized network, which you see we use meteorological forecasts to identify let's say the dispatching plan for the network, which is based on a load forecast on the production we have on site. It's also very important, the storage. And it has to be understood that the objective of this optimization is an economical one. So we have to ensure that we increase the economical performance of the operation of this network without clearly forgetting about environment and renewables and CO2 content objectives we have. So next one, please. So about load forecast, we have a module that we created ourselves in EDF. It's called REWARDHeat. It was first developed experimentally, and then we benchmarked this tool against other used models in the industry, and we have seen that we have pretty good results. So we have about a measuration of the forecast, which ranges about reaching 20%, which translates in about 5 to 6% economical gains. So we see that actually forecast helps us to better operate our network in a more efficient way. So this module uses different type of approaches. So it comes from the neural network, from random trees and others. And so it depends really on the problematic we have on site. And in the decentralization phase, when we look into decentralized substations, we really have to struggle with really specific loads, which sometimes are really complicated to be focused in a reliable manner. So this is the challenge we have to we integrate in REWARDHeat that we want to address. Next one, please. And then what's our optimization motor is, let's say, software is actually called Clever. It's also an EDF product. And the core of the system is really that we go into the system modeling. So we model all the parts of the system. We enrich it with a lot of techno-economic constraints, so ramp-up cycles, ramp-up costs, and so on and so forth. And we model all the fluxes between them. And the objective function is actually a system which is has to be understood under constraint optimization, which gives us the possibility to forecast in a day ahead way an hourly load and dispatching plan for the system. Next one, please. So my last slide, you have a glimpse of the network on the right side. So what are we doing in the project is that we are developing the modules, adapting it to the subject of decentralized production means. And we are designing actually the whole architecture of the system. So the SCADA on site, the automation system on site, harmonize it with the exploitation system, which is put on by Dalkia, and the communication with the forecast and optimization modules. So demonstration, we have to actually bring it online in next season, so in October 2021. About the PV system and the storages, we have launched dialogue with our clients. We have a little bit of delay due to the COVID situation, which have actually also stretched out all the election in France. So we are dealing with that, and we would like to be able to settle these things by end of the year, if possible, and have really a system design which works and makes sense for the client. And then energy performance contracting, we already signed an energy performance contract with the casino actually, and which we already integrated the notion of retributing him for the calories he injects into the system, and which actually enable us to ameliorate the COP during heating season for the other substation that cascade behind. So, well, that's all from me. Thank you very much.
Thank you, Christian, for an explanation of the application of seawater cooling and how it will be exploited in the REWARDHeat project. And so we're pretty short on time, so I will now move to our final speaker. So we have time for some questions at the end. Maria Victoria, can you please share your screen?
Okay. Hopefully you see my screen now.
Yes, I see it.
Okay. Okay. So thank you, Jack, and well, thank you for the invitation to participate in this talk. Well, in my particular case, I'm going to present very briefly, okay, with the street project, which is another H 2020 project funded by the European Commission, which deals with the renewable energy solutions for district heating and cooling networks. Well, I think it's quite obvious that the need of renewable energy integration in our lives. Just one quick picture about the EU status, the current status. You can see the heating and cooling in buildings and industry accounts for half of the EU's energy consumption. Unfortunately, around 70% of such energy is still generated from fossil fuels. Well, maybe you all know that the EU has a clear goal for 2050 and is to become climate neutral. So it seems that we should promote the use of renewable energy sources. And that's exactly why from the district project, we aim to develop, upgrade, and integrate a set of different renewable technologies that are applicable for district heating and cooling. You can see all the technologies that we're going to develop, and I'm going to give you some few words for each technology proposed. And in our case, we are designing and working with new concentrated solar panels for maximizing the sun's energy, which we know that is a free resource. 3 different technologies will be studied: an upgraded version of a PTC, parabolic true collector, and freshness panels, and a new innovative low concentration flat collectors. The aim is to reduce by up to 75% the cost of control and the tracking system, and also 25% the structures investment for the parabolic true and also for the Fresnel. And related to the low concentrated flat collectors, the objective is to improve production by 30% compared to other flat collectors, and also reducing the costs at the same time. Well, although we know that biomass is considered a renewable source, it's true that it's not fully clean, due mainly to the emissions, to the NOx emissions. So in the project, in the listed project, an innovative low pollution biomass boiler will be developed by designing a new furnace geometries and also integrating an innovative DeNOx system, combining selective and catalytic and non-catalytic reaction techniques. For the project, 2 different boilers will be developed. One is a high temperature, low emission biomass boiler, which will integrate new extra filters, and a second system that will be delivered to the demo site as a full package. Here, the objective is to reduce by 30% the current cost, by equaling the gas emissions. Another technology or combination of technologies is a hybridization of solar panels, solar photovoltaic panels, and the thermal system. With the combination, with the optimal integration, we can achieve an increase of 25% of the heat exchange efficiency. So that's with the optimized design and optimized integration. 2 different technologies will be also developed for cooling, for cooling purpose, fed by RES, by renewable energy sources. The first one is a renewable air cooling unit. This system is intended for HVAC applications, which can be fed by at low temperatures from a district heating or any other renewable heat source, providing cool air with a very, very low environmental impact, because here only air and water are required for the operation, and a very low energy consumption, since it doesn't use compressors. So, well, in numbers, the emissions will be reduced by 44%, and also we will achieve a reduction in electrical consumption by 80%, which is quite good. The second cooling technology is an enhanced absorption chiller with increased COP, coefficient of performance, obtained by adding a step of internal heat recovery. Currently, the COP for a simple effect absorption chiller is around 0.7, and in our case, we could achieve 1.42, which is almost double for a simple effect that requires lower temperature. A different approach for a waste heat recovery from data centers will be also studied here. In our case, will be based on the use of fuel cell, because we need to boost the temperature to be compatible with the current district heating network. Furthermore, this fuel cell, this technology, is able to provide both heat and electricity power, turning it into a cogeneration system. So we can provide electricity to the data center, and also this residual temperature for the district heating. Yes, when we talk about renewable energies, a key partner is the storage. In our case, considering the massive storage density, it is possible to store in much smaller space the energy provided by the solar panels, which is our example, by using molten salts for as thermal energy storage. So we will be able to reduce up to 20 times the volume of the tank compared to a conventional water storage, for instance. Yes, well, for the demonstration activity, other different conventional technologies will be integrated. These will not be developed in the project and will not be upgraded, but will be used and will be optimally integrated in the demo sites in order to complete the whole installation. And finally, well, yes, it's something that we have already discussed. We need something that optimally integrates, optimally controls the whole system. Here with district, we are going also to develop an advanced digitalization using machine learning, artificial intelligence, energy forecast. We are going also to develop an APP for the different actors involved in the district heating installation, or bidirectional wind integration, etc. Yes, the different technologies will be designed and manufactured, of course, but for being tested and demonstrated in 4 real sites. In our case, in Spain, in Romania, Sweden, and Poland. Some few words again for the Spanish demo site. Most of the technologies will be deployed and studied in a new district heating and cooling pilot in Alcalá de Henares. It's quite close to Madrid. The 3 solar panels, the 2 cooling technologies, the molten salt storage, and the biomass will be optimally integrated, with the main objective to maximize the huge amount of sun available in the location in Spain, well, in Madrid. For the Bucharest demo site, it's a different and inefficient section of the real district heating will be improved and retrofitted with a combination of the hybridization of the photovoltaic and geothermal installation. And also installation will be completed with solar panels for domestic hot water. In Poland, in Kuchnia Raciborska, a current district heating coal based will be retrofitted, in this case with biomass, photovoltaic system, and also heat pump for domestic hot water. Here, the full containerized boiler system will be delivered, as explained before. And finally, in Sweden, since, well, there the renewable energies are not very innovative, here the demonstration will be based on the extract heat from a data center that will be used for feeding the existing district heating in Luleå. As I said before, we need to raise the temperature, and this is why we integrate a new technology, which is the fuel cell, which is can be fed by hydrogen or biogas. In order to perform a wider study for the integration of district technologies, a complementary simulation activity will be carried out during the project. Different virtual demo sites will be simulated for that purpose, and different scenarios will study with district replicability towards 5th generation district heating and cooling. So we will study how to integrate our technologies, or most of our technologies, in not only for the 3rd generation, which is now more or less the current situation of our demo sites, but to study the 4th and the 5th generation as well. And yes, as conclusion, 3 main ideas, the 3 main results that I want to show you is one, of course, to show that we are studying different renewable solutions, 100% renewable solutions for district heating and cooling. Another main expected result is a set of replicable solutions, a portfolio for new and retrofitted district heating and cooling systems that can be from 3rd generation to 5th generation district heating and cooling. And last but not least at all, higher public acceptance thanks to an intensive awareness campaign and a dialogue with end users, which will be performed along the project, which I think that is a quite important activity. Yes, main numbers about the wood district project. So the funding is almost 50 million euros. The consortium is 21 partners from 9 countries. And you already know, we are going to demonstrate for real sites the 10 technologies developed with district technologies. The project is a 3.5 years project, starts in last year in October and will end in March 2023. And my last commercial message, in my case, we are on social media, so you can follow us in our Twitter, in LinkedIn. Also, we have a webpage, it's operative. And from here, I would like to encourage you to subscribe to our community of interest, which is in our webpage in the contact section. I promise that we are not going to spam you with a lot of mails, just 1 or 2 mails per year in order to give you the latest news and, well, to be in touch with you, what you think it could be great. That's all from my side. Thank you very much for the attention I gave, for the invitation. Here you have my email, my contact, just in case anybody is curious about the project and would like to know more about the project. I'm here, or the consortium is here for, yes, sharing with you our ideas. Thank you.
Thank you very much, Maria Victoria. So we're running a little bit behind schedule, but we still have time for some questions. So I would ask all the speakers to please turn on their cameras. And so the first question is directed to all of our panelists. So what are the technical requirements of 5th generation networks, and what are the challenges associated with meeting these requirements? So would anyone like to jump in and take that question?
Maybe I can.
Okay,
Herman.
Roberto, you go. Oh, I can.
No, Herman, you are.
Okay. Yes, well, we have a few features, and we were thinking about what is 5th generation then, and how it's distinguishing from 4th generation. So we had a few criteria, which are actually more like a vision where you want to go. It's a dot on the horizon where you want to go. So if you have buildings which need low temperatures, then we say we must try to use low graded sources as much as we can. And we might use some electricity, but keep it very small. The second one is close energy loops. So don't blow away heat or cooling from the roofs, but keep them in your system and make closed loops where you keep as much energy in your system. Then third point about those clouds of heat pumps that we make, but I can imagine other ways to do it, but at least the clouds of heat pumps give a very good way to integrate the power system into the thermal system of your city. So have a very high integration between electricity networks and the thermal networks. And then the fourth principle we have is that we raise those temperatures as far as we can, as close to the demand. So if you need domestic hot water and you have the 60-degree, try to do it at the point where you make this hot water. Actually, what we need from buildings is not too much. I would say insulation, because we need go down in temperature for the distribution systems in the buildings. But actually, it's not even that bad. So as I said, if we can insulate, save about 30% of energy from existing buildings, even the monuments, old buildings, that would be enough. I think much more important for future now is to speed up and to bring as less disturbance to those buildings. So if you have to move all the people out of their houses, that is big disturbance, and then we never do it before 2050. So we need to find systems which are quick and less disturbing. And then also we do some on the buildings to improve their insulation, but it's not like we have to do the major challenge on improving to zero energy buildings. It's not like that.
Great, thank you very much, Herman. And on the topic of buildings, what are the main obstacles to the successful integration of 5th generation district heating and cooling in existing buildings, and how can these challenges be overcome? Again, this is directed to anyone.
Yeah.
Roberto, please.
I think Herman already somehow replied to this, meaning that the main challenge is to bring these substations into existing buildings. So you must be fast. You must avoid making to introduce too much disturbance to the inhabitants. And again, this requires you to be fast and effective. And so, yeah, again, industrialization, prefabrication of this substation is really a key topic here.
Great, thank you very much. And the next question is directed to Christian and Herman, and it relates to business models. So what are the typical business models deployed for 5th generation district heating?
Honestly, for us, it doesn't really change the business model we put in front of the client. What we have as a big issue is we always have fixed connection costs, and we have costs for the kilowatt hour we provide you. But the issue and the obstacle we have is actual connection cost might be pretty higher because the system, as already said, are high in capex and capital expenses, which have to be reversed somehow into the network. However, in the operational expenses, I mean, we are much cheaper in the long term. So what the clients have to understand that, well, they have to put a little bit more force up capital, and that in the long run, this will be a win-win for everybody. As you might imagine that substation could be heat pumps, storages, maybe reversible heat pumps have not the same cost as a gas boiler. However, we're working much higher renewable share inside electricity costs, and together everything comes cheaper than gas prices. So this is actually what clients sometimes really have struggled to understand.
Yeah, it's the same for us. For first, the energy consumption is coming down because those buildings get better insulated, and then the cost for variable energy for the gigajoules is getting less for us because we do a lot from get out of the system and own generation of energy. So it's moving really to fixed cost, and then the system is a kind of provision, a feature which you add to the building. So you could say if I add 5 or 10% to the building investment, then I have heating and cooling for the coming 20 years. So we also try to make long-term deals and even based on square meter price. So if you have 10,000 square meter, you pay us maybe 10 euros per square meter per year, and you can use heat and cooling as much as you want.
Maria Victoria, do you have an input?
Yes, just from my personal point of view, I think that one of the most interesting business models in this case, and which can promote this 5th generation integration in the society, is the one that benefits the consumers, of course, who want to contribute to demand-side management. This means the prosumer business model, which I think is the most popular for this 5th generation, and this could engage public acceptance, which I said before is quite important, and encourage the prosumer model participation, where the end user could receive a kind of compensation, an extra payment or reduction in energy bills, or well, any other formula. But I think that this prosumer model could be yes, very well adapted to the 5th generation. That was my message.
Okay, thank you. And maybe one final question. How can heat pump technology contribute to the development of 5th generation district heating and cooling? So would anyone like to take that one?
That is key. I mean, if you want to recover waste heat or low temperature renewables into networks, then and you want to supply also your thermal energy at low temperature, you need heat pumps in the end. So they are key. And what we need is to have say units that are adapted to these applications, meaning that normally heat pumps work with air or with geothermal energy, which somehow are similar to what we have as a source, but they are not the same. So temperature level, mass flows, and everything is different, and we need to really have solutions that are adapted to these technologies, either from the waste recovery side or say the building side, so the final customer side.
And also from our side, what's pretty important that we have not just reversible heat pump, that we're also able to recover and make the, let's say, the link between symbiotic, same time heat and cooling needs, where you can grasp another 5 and a little bit more % of energy efficiency. So they are not pretty common in France, let's say. Maybe they are more common in other countries. That's why we really have to start to democratize them and use them more in a systematic manner. Because then if you ramp up all the substation and all the time you have your 5–10% recovery, well, it makes a difference in the overall business model.
Yeah, for us, I might add, we have a need for small domestic heat pumps, getting them cheap. If we are building clouds of them, there is also the safety aspect, so the Legionella. We want to make them smart also, so that we can get signals from those heat pumps in our central system if there is any trouble with them and a risk for Legionella, and that we get alarmed, and that those appliances serve us on this kind of information.
Great, thank you very much. And I think we'll wrap up the questions there. So there will be further collaboration between the REWARDHeat and We District projects later this year. So please join us at the Sustainable Places Conference for a workshop on integrating renewables in district heating and cooling networks. And finally, please also join us next week for the next edition of DHC Plus Talks, which will be brought to you by the Upgrade DH project. And the topic will be upgrading heat distribution and piping technologies. So we'll end it there for today. I'd like to thank all of our speakers for participating, and thank you to all the audience for tuning in.
Thank you.
Thanks a lot.
Bye.
Thank you so much.
Bye-bye.
Bye.